Hi, one more video for the central limit theorem, a couple of problems. Here's example 2, the lifetime of a TV tube. Is there even TV tubes anymore? Is an exponential random variable with a mean lifetime of 10 years. So here is the lifetime. Right, looks like that should be right at 0. Here's 10 years. Okay, exponentially distributed. F of x is the lifetime mean, so 1/10 e the negative x over 10 for x bigger than 0. Okay, so there's the density function. What's the probability that we just take a tube and it lasts more than 9 years? So here's 9 years, just shade that in. So that's the probability from 9 to infinity, 1/10 e to the negative x over 10 dx, which is e to the negative x over 10 negative from infinity, or 9 to infinity. So this kind of is bad language, right? This is going to go to 0. So this will just leave us with e to the negative 9/10, whatever that is. Now down here we're asking a different question. We're going to take 36 of these tubes, and we want to know, 36 different tubes, right? X1 is the lifetime of tube 1, X2 is the lifetime of tube 3, X3 lifetime tube 4, X36. And if we were to look at the lifetime of this one, this one, this one, this one, and averaged all their lifetimes, I'm going to call that capital X bar. What's the probability that the average lifetime is at least 10.5 hours? So the graph of X bar from what we were just doing should look like this, where the center should be the center of the distribution of any one of these, which was 10. So, if one of them has a lifetime of 10, this has a lifetime of 10, 10, 10, 10, 10. 10 of these times 36 divided by 36 is still 10. And then we said what would happen to the standard deviation is it should be what it was before. So the standard deviation for an exponential is 10 divided by square root of, we took 36, so this is 10 over 6. So now I want to know what's the probability that the average lifetime, that's X bar, for 36 is at least 10.5. But because we have normality, you could just integrate right on this curve, but I'm going to switch to a z-score. This is a probability that z is bigger than 10.5 minus 10 divided by, erased, 10 divided by 6. I get a number, go to my table. Okay, down here, same thing. This is test scores. I'm going to take 15 students taking the test. I want to know what their average length of time for 15 students, so this is going to be another X bar problem. Here's 4 is another X bar, 5 and 6 are on the homework. On the homework set 6. I thought I would add more, and here's example 7. So a physical quantity is measured 50 times. So we have something, we measure it 50 times. The average of these items is taken as a result. So I'm going to measure some 50 times. If each measurement has random error uniformly distributed over -1 to 1. So every time I take a measurement, equally likely the error is somewhere in this interval equally likely. So let's let E be the error. Error has a uniform distribution. A equals -1, B equals 1. We know the mean of the error should be 0, right? Because -1 plus 1 divided by 2, 0. Standard deviation for uniform, I think I still have this up. Here's a uniform, b minus a squared divided by 12. Let's see, let's go back to this. So b minus a, so 1 minus -1 squared divided by 12. This is the variance. So the variance is, let me see, 1 minus a minus 1 is 2, so this is 4 over 12, which is equal to 1/3. So here's the mean, here's the variance of a uniform. Okay, so standard deviation would be 1 over square root of 3. The question is, what's the probability that our results differ from the actual results by less than 0.25? So each measure, physical quantity is measured 50 times, and an average of these is taken. So this is a question about x bar. What is the probability that our results, so the average, differs from the actual value by less than 0.25? So what's the probability that x bar, the overall then average of these measurements, is between less than 0.25 would mean it could be off in either direction, right? So I'm just going to standardize again. So let me see, this is just minus 0, right? Minus 0 divided by 1 over square root of 3. 1 over square root of 3. So this is the probability that z is in between these two values, whatever 0.25 divided by 1 divided by square root of 3 is, and then I would use the z table again. I guess again what I want you to see is that x bar, again this distribution, is normally distributed. In this case I'm talking about the average, so the mean should be the old mean, and then again, I mean, if the distribution of these 50, it would have a distribution very much like this. This is the distribution of x bar for 50 error terms added together, right? That could be anywhere between, just very, very tight now because it's an average of 50 of them. So I hope this makes sense. If you need another video, another example, whatever, just let me know. Still in California for a while, so I still need to get you test 2 sometime soon. Okay.